Okay, well, let's begin. Welcome to Math 346, Elements of Linear Algebra. As you can see, I record my lectures. I post them on YouTube. I'll give you the guys the link later so you can watch it. Just in case you miss anything or you want to go over anything, you can always have this resource to look back on. So if you're here, this is Math 346. Make sure you need this class. The class is for math majors and computer science majors usually. But other students have the option of taking this class if they want a minor in mathematics. This is one of the classes that would count towards a minor. So a lot of engineering students take this as well. But if you are an engineering student, make sure you actually have 392 taken, because that's the linear algebra that you guys use for engineering. But this one is going to be a lot more general. It's going to be it has a fair amount of computation. So it's kind of a mishmash. It's called Elements of Linear Algebra, because we're not going to be studying linear algebra in all of its glory. But we are going to be getting into some of the theoretical aspects of it for sure. But also focusing a lot on computation. Not too much on applications because there's just not enough time, but I'll mention them as they come along. As well as for my linear algebra class in the spring, I literally just finished teaching. It's like continuing a bad dream. Well, I mean, I don't want my students to think I don't like hanging out with them. In terms of the grading, like I just finished grading this class yesterday. I hate grading so much. And now I'm here again, like no break. Okay, so last spring, which was literally about 2 weeks ago, I actually had a guest lecturer come and talk a little bit more about the applications. I don't know if I can get him to come back, but we'll actually see that. But we're mostly going to start focusing on the beginnings of the theoretical aspects of linear algebra as well as some computation. A lot of people, when they think of linear algebra, they think of working with matrices and things like that, and we will be working with those. But we're also going to delve more into what it means and why things work out this way and blah, blah, blah. So that's kind of what the course is going to be about. By the end of today's lecture, you will understand more about what linear algebra is as a theory, as something to be studied, and why you want to study it. But this is the class. You should be here if you're a math major, or you want to do a math minor, or you're a computer science major. Otherwise, I mean, if you're a math enthusiast, it's sure you're welcome. But just make sure that you're not doing this class thinking it fulfills a requirement when it doesn't. Make sure that you should be here. That's one of the things that I ask you on the questionnaire. Ever so often I have students come to me like in the middle of a class and be like, oh, I found out I don't need this class, so I guess I have to drop. Like they wasted all that time. So I just want you to be sure. The first thing we're going to do is we're going to go through the syllabus together. So you can't say no one ever told me. We're going to read it together. And we'll start off that way. Then we'll talk a little bit about the material, and we'll pick up with that tomorrow. So I'm the instructor. My name is Javon Smith. Call me Javon, is fine. I'll call you by your first names. You can call me by my first name. That's my email contact. I do have a college email that you'll see on my website, but I prefer my students to contact me via that email. I use my college email for other business. This is the website, so eventually I will post a web page for this class, and you can find it by going there. I'll also post a link to the YouTube videos, and you can go there and you can see it. The text we're using is Anton's Elementary Linear Algebra. This is what it looks like. So it's a very standard text. We've been using this text for like decades. It's now in its 11th edition. That's the edition that we'll be using. That's the location of the math department, the website for the math department, and this is the website for this class 346. If you go there, you will find things like the course description and as well as some past math finals, so you can do extra practice problems from. So here's some supplements. Be nice if you have the time. I mean, it's summer. It's going to be pretty quick, pretty intense, so I don't know how much time you're going to have to do much others. But sure, if you have the time and you're not getting everything you need from the book or in this class, you can go elsewhere. These are some suggestions. Calculators, a lot of this, a significant portion of this class, we are going to be doing arithmetic and stuff like that. But in general, calculators won't be allowed on tests or quizzes. although I might change that, we don't know. The grading chart, it's non-standard, so this is what we'll do. It's an 80 to get an A, right? So the A starts at 80. To get a C, you just have to break a 60. So that's already a hint to you what kind of course this is, right? Where I literally have to lower the bar by 10 points. I did the same thing for my class earlier. That's not standard though, but this class is kind of tough if you haven't seen this kind of material before, and especially in the summer. So I think that was worth it. The grade breakdown is, as you can see here, it's made up of 4 components. First, there's online homework. I will also be giving you suggested problems that we can find in a list towards the end of the syllabus. I'll talk about that in a little bit. But as far as homework to be collected, there's online homework that you're going to have to do. We're going to have to talk. I'll talk to you about that in a little bit. There's also a grade for participation. So you get 5% just for showing up. The eraser gets 5%. The chalk gets 5%. The blackboard gets 5%. Everybody gets 5% as long as you show up. So I will be taking attendance every day. So make sure you show up as well. I'll give 2 exams. So there's going to be one roughly at the halfway point, so around the end of June, beginning of July, hopefully before the last day to drop. And then there's another exam at the end of the class, and then a few days after that, there's going to be the final. So 3 exams total, but that's roughly going to be the spacing. And then there's a cumulative final exam that's worth 40% of your grade. And that, I had to make it 40% of your grade. That's the departmental policy. Final exam should be 40% of the grade. Moving on. No makeup, so don't miss any exam. Yeah.
Is it departmental final?
No, I write.
Okay.
Okay, but there are example finals. This is one of the few classes where it's not a departmental final, but the professor writes it.
You said 3 exams?
So 3 total, including the final. So there are 2 in-class exams, non-cumulative, but the final is a cumulative one during finals week. But it's the summer. Finals week is like right there. Like we finish class on Thursday and your final's gonna like the next Tuesday or something like that. So be aware of that. You have to really keep the gas pedal on. So attendance, I'll take attendance. I'll mark you late if you're late. Expect you to have an excuse if you're absent and support with documentation. Usual stuff about work ethic. Don't slack off, especially in the summer. You cannot slack off. Like we're doing the semester in half the time because the semester is usually around 4 months, but we're doing it in 2 months. But the fact that we don't have a break between the days is going to feel like it's 4 times as the speed. So you really can't slack off. Starting day 1, you have to start working and you can't stop. Okay, you don't have time to slack off and make up for it. It's not going to end well for you. So start studying today. Read ahead if possible. You'll see the topics. I'll talk about the topics we'll be discussing later. So you'll know ahead of time where we're going. So you'll know what to look up and what to do. Of course, you're responsible for your own grade. I expect you to be responsible students, mature students. This is a 300 level math class, which means you guys aren't new to this whole math thing. You've had college math classes before. I don't want to have to force you to do homework or force you to study. That's something I expect you to be able to do. And it's your grade. I mean, I'm assigning your grade, but really, you're getting the grade yourself. Like I'm just going to write down a letter that represents how much work you did. As I said, homework is online, but that comes with a warning. If all you do is the online homework, you're not going to do well, right? So the online homework is just for me to see that you're doing a bare minimum of work, and it can only really test you on the computational thing. We have yet to have an online grading system that can grade proofs. And proofs will be a part of this class. So you will be writing down arguments in sentences, writing paragraphs in English about mathematical concepts. Okay, so it's not just calculations that we will be doing. So the online homework alone is not going to be enough. I'm warning you. Okay, so we'll talk about how to actually supplement your study. To access the online homework, these are the instructions. This webpage is already set up, even though no assignments are currently due. So you'll go to this website. It'll be free to access it. You'll click on this, and you will log in with your CCNY credentials. So you'll put your CCNY. This isn't stapled. I'll also post an electronic copy of this on the webpage. Okay, so you log in with your CCNY email address, all lowercase, just the username part, and it will take your same password for the email, and you'll be able to log in. And whenever I see whenever I post a homework, you'll see it pop up. So you'll do the online homework there. I also expect you to remember the math that you've done before this class. Every now and then I will be taking examples from previous classes, even though that's not going to be the main focus. We are going to be focusing on a lot of material that will be new to you. But every now and then you'll realize how ubiquitous linear algebra is. Like, it's all over the place, and you've been studying it in various aspects your whole life and you never realized it. And we're going to reveal some of that. But I will be mentioning, oh, you remember when you did this back in that class? It was linear algebra. So I want to be able to pull examples from all over the place. So I do expect you to be, in general, basically good math students. Speaking of good math students, here's this paragraph is very important. I added this paragraph after I finished grading yesterday. So in my lower level math class, I have a bunch of mistakes that I call blasphemies, which are things that you should never do no matter what, because they're sins of very grave penalty. And so for this class, there's one, just as in the other class. You need to know your definitions, right? So a lot of students lost a lot of points, failed the final I was grading yesterday, literally because they didn't know the definitions, right? I was asking them, prove that this is that, but they didn't know what the definition of that was, so they did all this random things and were throwing ideas around, and like, you obviously don't know what that thing is. You need to know the definitions. You need to be very careful. You need to read them very carefully, and you need to know the definitions very well. Okay. Moving on. Contact. Again, you have my email, and I will be emailing you guys throughout the semester if announcements come up, if any advice or if I need to say anything to you. I'll also email you links to see an electronic representation of your current standing in the class, so your report cards. I will be emailing you a link to that, so you have to watch out for that email. I will use whatever email you have listed in Blackboard. So if the email you have listed in Blackboard is not a good email to reach you, you need to reach out to me and let me know, okay? Because that's where I'll automatically send stuff. I'm loading your emails from Blackboard. But I don't particularly like to use Blackboard itself, so I steal the emails from there and use my own thing. So again, feedback, I encourage feedback, make it constructive, so don't just be like, your teaching sucks! You can say, your teaching sucks because, I think we should explore this and do that, you can do this. But we're all in this together, I want you guys to learn, and while mistakes and issues are often repeated, no class is exactly the same as another class. So I expect you guys to have a different set of issues than other classes would. So you can let me know about those here. Also, there is help in the Marshak building, which is that building right across the street on the 4th floor. We have a tutoring center where you can get help for free from tutors there. It opens on the 11th, I believe, which is that Monday. So it opens on the 11th. The hours are Monday through Thursdays, 12 to 5. And probably not all tutors can tutor this class. They specialize in other courses. But I'm sure there are at least a couple tutors who can do this. So you can go there when it opens if you need extra help, and they will help you. A bunch of online resources that you can do. Did I mention it here? I don't think I did. Another resource. Especially in this class. It won't, the class I taught this morning it's not going to be that helpful for, but another resource that will be super helpful for this class is Wolfram Alpha. Does anyone know what Wolfram Alpha is, or have you seen it before? All right, so you can just go to wolframalpha.com. So it's by the same people who built the math programming software called Mathematica, I think. But it's very nice. You can actually use it for this and many other classes. So you can go there, especially if you want to check your work, do extra practice. You can go here and check your answer. You can enter questions and it will give you an answer. So for example, we'll be talking about things like matrices, so there will be things like, say, 1, 2, 3, 4, rectangular array of numbers. Talk about that in a bit, right? So I can ask you, for example, to say multiply two matrices, like 1, 2, 3, 4 multiplied by 3, 1, 0, minus 1. You'll learn what that means soon, but for now you don't have to worry. What you can actually do if you want to check your answer, you can go to Wolfram Alpha, you can actually enter this in there and it will give you the answer, right? It has a certain notation though. Something like this, something like an object like this, you would write it as, you put these squiggly brackets, inside the squiggly brackets, put another pair of squiggly brackets, and you list the elements of each row. This is called a row. So you list 1, 2, and that you just define the first row, comma, 3, 4. You just define the second row. And then when you put the squiggly brackets around all that, that's a matrix. Where this is the first row, that's the second row. Then you put multiply, which is the asterisk. And then you put 3, 1, and 0, -1. And press enter and it will actually give you the answer. All right, so it's a nice thing to check your work. A lot of things in this class will be computational, and you can actually use Wolfram Alpha and other things like it. Symbol Lab is another one. Although I don't use that much, but I know a lot of students who've been using that. That one you can enter things sort of like a template, so you have to know less programming. This can understand a lot of things in English language, just regular English language, but it's not a template-based kind of thing. So you do have to know some sort of programming jargon. But Symbol Lab, you can actually enter things as a template, and it will help you compute things. So you have a ton of resources all over the place. And linear algebra, as I said, it's very, it's all over the place. So you'll have a lot of resources for this class. Usual rules: silence your cell phones, no eating. You can drink, but remove your garbage. Academic integrity policy: don't cheat. If I catch you cheating, I will take steps against you. This is some important dates. You can view the full academic calendar at that website. Yeah, so it tells you about when you can drop a class and get a refund and all that stuff, as opposed to when you can change classes and when the college is closed. We have 1 day off, but you guys will of course all be studying anyway, which is July 4th. But I don't even know why I mentioned that. It probably shouldn't make a difference to you, but we won't be here. So the final exams will be on the 24th. I actually listed that on the very next page. I tell you when the final exam is. So we move on to the next page. So this is the list of topics that we will be going through in this course. So we're going to talk about all this stuff. So the first section here is going to be pretty computational. I'll be doing proofs here and there, but after that it gets very theoretical, and mostly what we'll be doing is theory and with sparse computations about here and there. So these are some suggested problems. As I said, going through the online homework alone is not going to be enough. So you should practice problems from here, especially if you want to practice proof problems. There are some of them in this list here. So there's a mix of computational and proof-based problems in this list of problems here. So you should go through that and do more. If you're not getting something, do more than the list of assigned problems here. But that's like the minimum. I would say that you should be doing this anyway, pretty much mandatory, but I'm not going to collect it. So, but if you don't do it, it's going to be your loss. You're not going to do well, right? This is not the kind of class where you can just come in and sit down and watch me do stuff and you'll get it, or just do the online homework and you'll get it. It's just not going to work. Last page is a questionnaire, anonymous, so you can throw it out and just attach it and leave it with me when you leave the class. Before I move on, any questions, concerns? Yeah.
Is the applications version of the textbook okay?
Yeah.
Okay.
Yeah, because the applications version is just the textbook with an additional chapter, I think. They add 1 or 2 chapters at the end. Yeah, so as long as you get the 11th edition. I mean, the difference between this and like the 8th edition when I took the class is not that much, but the problems might be in a different order. So I'm not. The Tutoring Center might have a copy of this, but I'm not sure.
What do you think of the Gilbert Trang's textbook as a resource?
Yeah, definitely. I believe I mentioned it. Didn't I mention it? No, but that's good. That's actually a good resource. That one is a lot more theory focused, I think. The organization is going to be different, but if you want to use it as a reference, I don't mind at all. Some instructors use that textbook, but this one is more standard. Other questions? Concerns? Okay, so you guys can fill that out, and I'll collect that towards the end. In the meantime, so our class ends at 3, so we have an hour and change. Okay, so let's not waste it because it's the summer. Let's actually get started. So what we're going to be talking about for now is the section zeros, which it's section 0 and there are no problems because technically it's not a part of the course, but it's kind of unfair that it's not a part of the course. So this course will be expecting you guys to be able to prove things and do all sorts of things in mathematics that the prereqs for the course don't prepare you for at all. So that's why I put in the section 0. So I'm going to give you some ideas on things that you need to pay attention to, that you need to be aware of, that you need to be able to do on my own, because somehow they'll expect you to know how to do this, even though, yeah, I believe the prereq for this course is Calc 3. It's not going to be good enough to help you with proofs. So what we're going to do is we're going to talk about some mathematical ideas. I'm also going to give you basically a mini crash course on proofs. So I'll spend 1 or 2 lectures just talking about how to prove things. So basically the class that you're in earlier, I'm going to teach you that entire class in two classes here. So I'm just going to give you the quick highlights. This is what this means, this is what this means, okay, blah, 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 blah. And you'll go through still very quickly, but slower. So I'm going to do like the 3/4 of that course in like 1.5 classes here. But so that's gonna be fun. But it's going to be an important thing that you need to know. But first, let's actually start with lecture 0, which is the intro to linear algebra. Let's actually set the stage. To figure out what is it that we will be spending the next 2 months doing. So let's talk about some preliminaries. So there are lots of objects I need you guys to be familiar with. So let's start with those. Let's talk about sets. Definition. A set is a collection of objects. They're called the elements of the set. Notation. These squiggly, does anyone know what those are actually called?
Curly braces.
Huh?
Curly braces.
That's what they call them? They're called curly braces?
That's what I call them.
They're all brackets.
They're brackets, but I don't know what the
I think
the
they call
prefix of this is.
square
But that's the symbol. So you can write this symbol and you can literally list the elements that are in this guy. So I can say, listen, a set that contains 3 elements, right? So this is the name of the set. It's usually an uppercase letter, though not always. Just be aware of the definition. It has 3 elements. One, 2, and 3. So this is a set containing the 3 elements. We can Sometimes sets are very large and you can't list everything, even if you know pretty well what the set is. So there are other notations that will come in handy. So the use of ellipses, for example. So I can 1, 2, 3 to 1,000. So here's a set containing all the whole numbers from 1 to 1,000. I just don't want to spend the time writing it down, so I use ellipses to show that obviously there's a pattern. You use this when there's a clear pattern for how to obtain the elements of your set, but you don't want to list them all. You can write ellipses as long as that is understood. So this is the set of all integers from 1 to 1,000, inclusive. You can also talk about putting ellipses at the end and just closing that, which means that the pattern continues indefinitely and there is no stopping point. Keep going. Right, so this is the set of all positive integers. Positive means it's bigger than 0, negative means it's less than 0. 0 is neither positive or negative, it's called a non-negative number. It's the only non-negative number on our number line. So use that notation, use ellipses whenever there's a pattern towards obtaining your elements that the reader will understand, you can use ellipses. We can also define sets by conditions. So I can say things like C is a set of all x such that so I can give you a condition for how to create a set. You'll notice that this set here is actually, I was going to say it's equal to C, but even if I called it D, you'd realize that this is actually equal to C, right? So I can express this set in terms of a condition rather than even writing it down as a list of elements. So sometimes, even if I can know what elements there are, I might not be able to write them down in some way that the reader can understand. You can always do some sort of condition. Another thing you want to know is about the members of a set. So there's this symbol, that means a member of or an element of. So for example, if I had my A equals 1, 2, 3, I could say 1 is an element of A. I could also say something like 4 is not an element of A. Typically in mathematics, if you want to say it's not something, you can like strike through it. Kind of like if you have equal versus not equal, you can strike through it. So I can say this is an element of A, and that's not an element of A. Another example. Here's a set. All the way up to 1,000. Define f to be equal to the set of all x in E such that x is greater than 998. So here I defined a set, and I defined another set that talks about that set, and elements in that set. What would that set be equal to?
999 and 1000.
999 and 1000. Right? So I just put a condition. I created a set by selecting things from another set that fulfills some condition. Right? By the way, just to mention it, you could write this notation, which is whichever notation you want to use, I don't care. Instead of that bar, you can put the colon. And it has exactly the same interpretation. Right? So this is, it's read such that. So I can say F is the set of all elements that are in E such that the element is greater than or equal, greater than 998. F is an example of what we call a subset. So that's a definition. Is a subcollection. So you can have a collection of things, but sometimes you don't care about that entire thing. You just care about some kind of sub-collection of that thing. If A is a subset of B, we write this symbol. A is a subset of B, but it is known that A and B are not the same. We write that symbol. Right? So there's a symbol where there's a bar underneath and there's a symbol without the bar. Or some people, not many people use it, they'll do this and then they'll strike out the bar. In the latter case, A is called a proper subset. So if you're a subcollection but you're not the entire set, you're not equal to the entire set, you say you are a proper subset. There are some important sets. First one is called this or that. This is called the empty set. Or the null set. It's the set that contains no elements. Right? So it's an empty subcollection. So sets like that arise when we do things like, okay, here's a group of elements. I want to select elements from that group, from that collection, that fulfill some condition. But what if no one fulfills that condition? Then your collection, the subcollection, has nothing in it. Right? So you end up with something that's called an empty set, and that's the notation. Okay, so this is called the empty set or the null set. It's a unique, right? So all empty sets are considered the same. It's also, you should also note that the empty set is a subset of A for all sets A. Given a collection, you can always create a collection by choosing nothing out of that collection. It's also true that a set is a subset of itself for all sets A. Given a collection, you can create a rule that literally chooses everyone in that collection. So you can choose to get the set again itself. other important sets. There's the set n. We call these guys the natural numbers. These are just the whole counting numbers. We will define it as the positive integers. It may include 0 depending on the source that you're reading from. So usually if a textbook is using the natural numbers, there will be some sort of, in the introduction or somewhere, they'll tell you which definition for the natural numbers they're using. May or may not include 0. These are called the natural numbers. Right, so the whole counting numbers, we call those the natural numbers. If you want to include 0 and the negatives, you get this set, the set Z, 0, plus or minus 1, plus or minus 2, plus or minus 3. All right, this is the set of integers. Which is the set, the collection of all whole numbers, whether they're negative, positive, or 0. There's a set Q. This is a set of rational numbers. It's hard to write down a list that would describe this accurately, so you describe it by a condition. It's a set of all things that look like A over B, where A and B are integers, and B is not 0. These are called the rational numbers. Or, as you might have affectionately known them as, the fractions. So I can also define what we call R, which is, it's hard to write this down in a description, the set of all numbers on the number line. So especially in this class, we're going to rely on a very intuitive definition of this guy, or the set of all decimal expansions is another way you can think of it. We're never going to define this set precisely in this class, but it kind of has an intuitive feel to it. Hopefully you guys all know what the real numbers are. It's called the real numbers. Yeah, they're fake numbers. No, it's just called the real numbers. By the way, you can note that, for example, Q is a subset of R, right? You can write that down. That is something that's meaningful to say, right? So I can take the real numbers, the set of all numbers on the number line, and I can pick out the fractions, and that's creating a subset. I cannot say R is not a subset of Q, right? Because there are elements in here. This guy has elements that that guy doesn't have. Oh, by the way, can I say Q is a member of R? No, it's not a member of R, right? There's no number in the real numbers called Q, right? C is called the complex numbers. Basically, a lot of times you want to solve polynomials, find solutions to roots of polynomials in R. There is no answer, so we created another set that fills in the gaps to solve polynomials. This is Q. Turns out that this is C. Turns out that this set is insanely useful in its own right and gave birth to a whole other branch of mathematics called complex analysis. We're not going to get into it, but it's the set of all numbers that looks like A plus IB, where A and B are real numbers. And with this set, we can solve, in theory, we can find the solution to any polynomial. So I can look at the polynomial x squared plus 1, set that equal to 0. There is no solution in R that solves that equation, but there's a solution in C that solves that equation. Where IO is just a number we invented to call the imaginary number, which when we square it, we get -1. So these are very common sets. One thing that we'll use here, you might seem to write down a lot, is F. Basically, if I write F, this means R or C. Right? Meaning, if I want to make a statement that works for both the real numbers and the complex numbers, I will instead write the letter F, bold F. We'll use the symbol, just fancy F, for a field. Don't worry about what a field is, but intuitively, this is a set with two operations. That behave like the real numbers. Okay. In fact, if you condense all the properties of the real numbers and you think about everything you can do with real numbers, if there's another set that you can do all that stuff with as well, that has two operations similar to multiplication and division, you call that a field. Okay? So, for example, you can take a real number, and as long as the other number is not 0, you can divide by a real number, right? I can take 1 and divide by radical 2, and I can create another real number by doing that. But if I'm looking at integers, right, I take the integers, the set of integers. If I take the integer 2 and I divide it by the integer 3, do I create an integer?
No.
No, which means that the integers are not a field. They do not behave like real numbers. Okay? So Q is a field, R is a field, C is a field, the integers is not a field. The natural numbers, not a field. All right, so that's basically going to be the intuition behind it. You study things like that in greater detail in a class called Abstract Algebra, but we're not going to do that here. Why we need to know about fields is that we're going to be focusing on things called scalars. And they're going to be very important in our definition. The elements of a field are called scalars. Elements of a field are very good to denote scaling of some sort, to talk about the magnitude of something. Pretty much elements in a field are pretty good at that. But if it's not a field, it's not that great. So I'll talk about scalars later on. They're called scalars or constants. Another thing we need to review, functions. So I'm going kind of quickly, but it's because I think most of this you should have seen already. So the notation here, you name functions usually with lowercase letters. For emphasis, you can have that notation. This is a function from a set A to a set B. Okay? So these are two collection of objects. I'm creating a function that goes from one collection of objects to another collection of objects. Its name is f, right? F is the name of the function. So this is the notation for a function. Now a function is a rule that makes assignments between collections of objects. So A is called the domain of the function. B is called the codomain of the function. The function is a rule that assigns to each element in the domain exactly one element in the range in the codomain. So I said range definition. If I take all the elements that are the so-called outputs of a function, and I can create a set from them, the range of the function is the set of all elements in the codomain that are assigned. So I can say A is the set 1, 2, 3. B is the set 4 and 5. Let's make one. 6, 9. So I can have two sets here. This is A, which is the domain, that's B. And let's say I created a rule that takes 1 and it assigns it to the number 4. It takes 2, assigns it to the number 5, takes 3, assigns it to the number 6, and the 9 is just hanging out here. A is called the domain, B is called the codomain. These three elements here are the range, right? Notice that 9 is not in the range. Okay? Here, these are the symbols, the domain of F. I can say this is the set 1, 2, 3. I can say the range of F. This is the set 4, 5, 6. And notice that 9 is not in the range of F. So a function is just a rule that makes assignments between two collections of objects in such a way that there's only one connection to each individual object. So you can have a function and it can look like this. That's a function. I can have each of them going to unique guys over there. That's also a function. However, if I have something that does this, has one element connecting to two elements over here, it's not a function anymore, right? Because it made two connections from the domain. A function is required to make one connection. Okay? So an example of something that would do this is a circle, right? Take the circle x squared plus y squared equals 1. Then if you plug in like x equals a half, there'll be two y values that outputs, right? So the example here is a circle. And the example here, something like f of x equals x plus 1, which is a rule that we have here. Have I said anything strange about functions so far? Yeah?
I just have a question, I guess for your other class as well. Say that you
Oh yeah, we're gonna do this like chapter 9.
Right.
Like this is way
Yeah.
down in the other class.
So say that you give like a definition, right? And could I use some other like variation of the definition, assuming it's correct though? Like everything like is works.
If it's logically equivalent, yes.
Okay.
So when we go through chapter
Okay.
2, you'll understand what logically equivalent means.
Okay.
But there are various definitions of functions, but that's probably the best one we're going to use here. An important notion for functions is one-to-one. A function f is called one-to-one or injective written one-to-one for shorthand. If each output of the function i.e. and here's the definition that I would use for one-to-one, and this is something we're going to be proving at some point, whether something is one-to-one or not is something we're going to care about greatly. If the outputs are the same, if my f of x equals f of y, it must mean that my x was equal to y, right? If I get, this output can only come from one input, right? So this is an example of a one-to-one function. If these two outputs are the same, they had to come from the same guy. So that's the definition. Another equivalently, you can say that if the inputs are different, then the outputs must be different. Right? That's easier to see in this picture, right? This is a function, but it's not one-to-one, right? Because here I have different inputs going to the same output. This is a function that is one-to-one. Different inputs go to different outputs. Do an example. F of x equals x plus 1 is one-to-one. Proof. I'll talk more about proving things later as well. Assume that f of x is equal to f of y. This means, what is f of x?
X plus
What is f of y?
1 plus 1.
That means that is true. Which means I can subtract 1 from both sides, and I get x equals y. This means f is one-to-one. So here's an example of a proof. I have a definition. I have to show that this function fits that definition. If I assume the outputs are the same, it's the same as assuming this equation. And I can show through logical means, in this case subtracting 1 from both sides of the equation, that the inputs have to be the same. So I've proven that this function is one-to-one. I can have an example here that says g of x equals x squared is not one-to-one. Proof. How do you show that something is not one-to-one?
Counterexample.
Counterexample. You can just tell me an example where it doesn't work. Right? Note, g of 1 is the same as g of minus 1, but obviously 1 is not the same as minus 1. So it turns out that the first statement is true, but the inputs are, I have the same output. These would both be given to me 1 as the output, but I got that from different inputs. Right? So there isn't just one thing that maps to the output. There are two things that map to that output. Right? Two or more. Right? So that's not a one-to-one function. We'll talk about another definition. Function f is called onto or surjective if for every element in, let me say what this is going from A to B. It's called onto. For every element in B, there is some element in A such that for every element, let's call that y, there is another element x in A such that f of x equals y. Meaning everyone in your codomain is actually in your range. I.e., the codomain is equal to the range. I gave you an example earlier that showed that this is not always true. Right? I gave you an example of a function here where 9 was not in the range. Right? But if everyone in your codomain was assigned by the function, you call the function onto. Function that is both one-to-one and onto is called, does anyone know what that's called? Bijection. So you can talk about a bijective function. We're going to look at a very important kind of bijective function called an isomorphism towards the end of the class. So this is just a function that is both one-to-one and onto. It becomes an isomorphism when I throw an additional property on top of it. So this is called a bijection. Example. Let FB go from R to R. Then f of x equals x plus 1 is onto. Why? So let x be any element of R, the codomain. Then you can notice that x minus 1 is also in R. So I have shorthand. And here I'm thinking of R as the domain, such that if I take f of that number and plug it into this function, if my f of x is x plus 1, what is f of x minus 1?
X.
Right, but I want to show this x plus 1, right? Just replace the x with the guy in here. That simplifies to x, right? So for any number in my codomain, there's a number in the domain who gives that number as the output, right? To show you that this does not always happen, let me give you another example. Say f of x equal f, again, we use g. Let g go from R to R, where I define my g of x to be x squared. This is not onto. How do we know that's not onto?
The negatives.
The negatives, you will miss all the negatives. Since -1 is an element of R. Now I'm thinking of R as a codomain. But there is no x in R, the domain, such that x squared is equal to -1. There is no real number that will solve that equation. Therefore, this function is not onto. There are numbers that it will miss, right? So I would have the set R here and the set R here, and I have all the positives over here and all the negatives over here, but all these functions are going toward the positives and 0, right? Everyone in this function is going into that collection no one in here is getting any love, right? So that function is not onto, because there are things in the codomain that are missed by this function. Turns out that this function is both one-to-one and onto. This is a bijection. So you've definitely seen functions before, but you've probably not spoken about onto and one-to-one in detail. But you do know how to identify them. So in like Calc 1, you probably spoke about onto and one-to-one, where there was like, oh, it's just a function that passes the horizontal line test. That's just a fancy way of saying, each x value only has one y value. But in this class, we can't have rules like that anymore, because we'll be talking about things that you can't visualize all the time with a graph. So you have to understand what the definition of something is in terms of a mathematical statement rather than a picture. And you need to be able to argue about whether or not something fulfills a condition. Okay. By the way, note. If f is bijective, it has what we call an inverse function. Bijective functions have inverses. Functions that are not bijective do not have inverses. So this is one reason why we care about bijective functions, the fact that they have inverses while no other kind of function does. We denote these. If I know a function is f, then its inverse function is denoted by f to the negative 1. So it doesn't mean the negative 1 power, it's strictly speaking a notation. Okay. F inverse is a function that reverses the rule for f. i.e., if f goes from A to B is a bijection, then f inverse will be a function that goes from B to A, so that if my f of x, the output was y, then if I plug in the output into the inverse function, it gives me back the original output. It undoes the rule. So my function does one thing, and the inverse function will reverse that thing. So I can have a function, right, here's my x, it connects it to an element called y, and that is done by some function which I call f. If I want to undo this process and go from here and get back there, I can do what I call an inverse function. And by the way, that can only be done if your function is bijection, right? One reason why, if you can see that, let's say I had an element here where it's not one-to-one connecting to this, and you give me this, could I tell you who that came from? The answer is no. There are multiple, without additional information, I can't tell you who that came from. There are 3 guys that could have come from. It's not a defined function. A function has to be a rule by how I know how to assign things. In this situation, I won't know how to assign things, right? Or you can think about a function that's not onto. All right, let's say both guys connect to this. Who does that guy get assigned to? No one. It can't be a function. So if it's not one-to-one or it's not onto, you can't actually create a function in the opposite direction. It has to have both the properties of one-to-one and onto to be able to do this. Definition. function is called a linear transformation. Function, let me give you a label. F from A to B is a linear transformation. That's a phrase that we will define now. If the following conditions hold. If f of x plus y is equal to f of x plus f of y. So that's one condition. The second condition is f of k times x is equal to k times f of x. Where x and y are elements of A and k is a scalar, meaning the element of a field. Any function that fulfills these two properties, we call this function a linear transformation. Can anyone tell me about a function that's a linear transformation from R to R? Yeah?
The derivative?
The derivative does work. Yeah. That's getting more general. We're getting there. We're not there yet. I just want a simple formula. Give me a function with a formula. F of x equals, give me some formula.
X.
X. Right? Let's make it a little bit more challenging. Let's say just 2x. So it's not just a totally silly example. Is a linear transformation. Okay, here's a challenge. Can you give me a linear function that is not a linear transformation? Oh, G. That's my counterexample guy. I want to justify the fact why I'm going to create a whole new kind of function. And the word linear is not enough. Tell me a linear function that's not a linear transformation.
X plus 1.
X plus 1. In other words, or let's make it a little bit more complicated, 2x plus 1. You add a plus 1 and you kill these properties. Let's see. Proof. F is a linear transformation. We have to check two things. Right? One, that f of x plus y is equal to f of x plus f of y. And two, that f of a constant times x is just a constant times f of x. So let's actually go through and show that that is true based on the definition. Note, f of x plus y is, if my function is 2x, what is f of x plus y?
2x plus 2y.
2 times x plus y, right? Just replace this guy with x. But that is equal to, I have the distributive law, that's 2x plus 2y. But that is equal to, what is 2x? That was just f of x. And what is 2y? That is just f of y. So it fulfills the first property. second property.
Also, f of kx, x is just a scalar here.
This is equal to what? 2 times kx. But we know that multiplication on the real numbers is commutative, right? Doesn't matter what order I multiply in. I can switch this k and the 2. But that's just k times, what's that? That's k times f of x. This means f is a linear transformation. Let's look at g, which looks very similar to f. All we did was add a plus 1. But I claim that that actually messes everything up. Claim g of x equals 2x plus 1 is not a linear transformation. Proof. Let's look at g of x plus y. What is that equal to? It's 2x plus y plus 1. That is 2x plus 2y plus 1. This, of course, here is f of y plus, what is this?
f of x minus 1.
It's not f of x is the important thing. It's not f of x. Right? So I took g, oh, sorry, not f, g. So it turns out that if I take the function on a sum, it's not the same as the sum of the functions. Okay? So it's not a linear transformation. It fails, right? And you can stop the proof right there. But you'll see that the second rule also will break if you do this. Just do it, wait until
You know I am.
yeah, just wait until so this is not a linear transformation. So functions are going to be important, not immediately, but later on, especially when we get to chapter 4. Knowing when a function is one-to-one or onto is going to be important, knowing when it's a bijection. You'll also need to know when a function is a linear transformation from when it's not. Spoiler alert, linear transformations kind of look like what you expect. They look like linear functions like planes and tangent planes and straight lines. The only caveat is, to fulfill this definition, they have to pass through the origin. Right? So the fact that 2x passed through the origin is why it was a linear transformation. 2x plus 1 does not pass through the origin. That's why it was not a linear transformation. Turns out containing 0 is going to be a very defining characteristic of a linear transformation. Let's talk about something else. I know I'm throwing a lot at you, but I'm kind of setting the stage at 3. I don't want to give you we'll define in more detail later. I'm just going to give you some basic ideas. What we call a vector space. So you'll notice that in the syllabus there's a whole section of topics that we're going to do that falls under vector spaces. Right, so I'm going to tell you what a vector space is, and we'll come back to it in detail when we go to chapter 4. So with two operations, plus, which we call addition scalar multiplication. Such that the following hold. So the word vector is familiar. So can anyone hazard a guess as to what a vector space is? An example of one? What would you guess a vector space is? Example.
Align with the direction.
Huh?
Align with the direction.
Align with the direction? Well, that would be a vector. I'm talking about a vector space.
It's a plane.
Huh?
A plane?
A plane that passes through the origin is an example of a vector space. An example from Calc 3, R3, the three-dimensional space is a vector space. R2 is also a vector space. The real numbers itself is a vector space. R is also a vector space. So it's just a set on which we have two operations which we call addition and scalar multiplication. An example you would be familiar with is the set of two-dimensional vectors or three-dimensional vectors. But it's going to be a lot more general than that, and that's going to be a rule in this course. We're going to take things a lot more general. You've seen specific examples, but we're going to talk about things in general. So it's just a set, let me call it V, that has the following properties. And if you look back at the properties that you took advantage of in Calc 3, you'll realize, oh, okay. So we're connecting the familiar with the more general principle here. If we let these guys be, let's say x, y, z are elements of V, and let's say k and l are scalars, then here are some things that we could do with vectors in R3 that we're going to be generalizing. 1. If x and y are in the set, it turns out if I add them, they're also in the set, right? If I take two three-dimensional vectors, I add them together using the laws of addition, vector addition, I get another three-dimensional vector. So adding two things in the set gives me another thing in the set. 2, addition is commutative. This property is called closure under addition. Meaning when you add two things in a set, you get another thing in the set. The second property is the fact that addition is commutative. That means it does not matter what order you add things in. The vector x plus y is exactly the same as the vector y plus x. 3. Addition is also associative, right? Meaning if I have 3 vectors, I can add 2 and then add it to this guy, but I can also move the parentheses, add the first 2 and then add to the third, and I get the same thing. 4. There exists an element in V denoted by this symbol, which we call the 0 vector. Such that the definition is not going to be the guy that has zeros in all the components, even though in R3 that's your example. But this is what defines the 0 vector. This is what it means to be a 0 vector. It means that if I take x plus 0, it gives me x. And obviously if I take 0 plus x, it gives me x. For all x in B. Any element that does that is called a 0 vector. In R3, this was just a vector that had zeros in all the components. But it might look different depending on the context. So there's the existence of such an element. in the set, which is why you had to have a plane passing through the origin to be a vector space. 5. If I take the scalar k times an element, that is in the set. So if I take a vector and I multiply by a scalar, it's still a vector, right, in the R3 sense. Turns out that it has a distributive law. I'm using x and y. So I can take a scalar and I can multiply by a sum of vectors, and that would give me it has a distributive law. It also has a law that distributes vectors among scalars. So I can have a sum of scalars times a vector. And that will be true. I also have commutative multiplication of scalars. So if I have k times L times x, it's the same thing as k times L times x, which is the same thing as, we can swap these two, which is the same as L times k times x. You can do this manipulation with scalars and associativity. Another property. One times x is x. Seems trivial, it's not that trivial. We'll get into that. 1 here denotes what we call the multiplicative identity. It is the scalar in our field for which when we take the scalar multiple of our vector, we get itself. The last property that defines a vector space is the existence of negatives, or additive inverses, for every x in V. There exists an element minus x in V such that if I take x and I add it to minus x, the result is the additive identity. Minus x is called the negative of x. These 10 properties worked on vectors as you know them in Calc 3. And these 10 properties are what we define to be a vector space. At this point, which we'll see later, you can use some intuition from Calc 3, but you really want to get away from using that intuition because we will be talking about things that are far more general than just vectors. So these vectors can be anything. They can be functions. For example, the set of continuous functions form a vector space, right? I can add 2 continuous functions, get a continuous function. Doesn't matter what order I add them in. This would also work. The function f of x equals 0 serves as the 0 vector, right? If I multiply a continuous function by a number, it's still continuous. The distributive law holds for continuous functions. If I take a continuous function, just change all the